Hello guys. We are continuing our lecture series. That is, a lecture which we have started on the strength of material. And in today's lecture, lecture number 5, we're gonna discuss buckling of columns. Right now, before discussing the buckling of column, we must understanding the few fundamental thing regarding this buckling of columns. Now, as of now, you can see this figure. There's a long rod, cylinder rod, a prismatic rod, you can say. Prismatic means same cross-sectional area throughout of its length, right? If I just consider the length L, so same cross-sectional area is there, right? Pi by 4d square, or maybe if it is a square cross-section, then whatever the dimension is square, that will be the cross-sections area. That is same throughout of its length. And what you are observing, this long cylinder member is subjected to axial compressive load, right? Because of the axial compressive load, when the load is reaching to the particular value, that particular value we are calling critical load. That particular value we are calling what? Critical load, right? Now, if it is reaching to the critical value, and when you are applying the load beyond the critical value of the load, then the column or that particular vertical rod will be there, that will be buckled or bent about some axis. This bending phenomena is a very severe phenomena, my dear friend, in case of columns. Now you might be thinking, sir, we might be discussed the bending in the beam also. Like if I just talk about the beam, then suppose this is the beam and we are applying some kind of load. Then what are the deformations and what were the deflections you might have seen? So this was the elastic curve that we framed, and here we have said that okay, this particular deflection must be less than the permissible one, whatever the maximum deflection is there, right? PL cube, or maybe here W load is there divided by 40 ATI. So whatever this value is there, that has to be a permissible limit. There we don't say this as a failure one, but even though whatever amount of bending will happen, whether it is a permissible or maximum or small, we say that the column has been buckled. And this phenomena where the buckling is happening, bending is happening about some axis, we say it's a failure of columns. We say it's a buckling of column. We say it's a failure of column or buckling of column, my dear friend, right? Here, so we must protect the beam or whatever the column is there to buckle it. So for that, if you just ask to basically one layman, just how can you avoid the buckling? He will say, don't apply the load beyond the critical load. So what is this critical load, which is much more important than anything to discuss about in this chapter? Now let's focus our attention on this critical load, and what is the formula for the critical load? Let's discuss about this. So very first thing is that a long cylinder member is subjected to axial compressive force. A long cylinder member which is being subjected to axial compressive force are called as columns. And whatever the lateral deflection would be there, my dear friend, whatever the lateral deflection would be there, that lateral deflection would be called as a buckling of column. The lateral deflection will be called buckling of column, or we say it's a failure of column. This buckling shape is what? Just like a very similar to the sinusoidal function, right? You will see that full derivation, then you will realize that how this deflection curve is happening. Why not is it is deflecting some other by some other, basically by some other profile, maybe like this. Why not something like this? Why only something like a sinusoidal function? That will be decided by the whatever the derivation, basically what we did for our column analysis, buckling of column analysis, right? So one thing is sure or guarantees that we have to apply some kind of what? We have to apply some kind of what? Load, which is much more than critical load. Second is it has to be an axial compressive force, not tensile force. Tensile force will never cause a column to buckle, right? Now, to understand the stability of the column, why the buckling is happening, how the buckling phenomenon is happening, let's try to correlate with this topic with a little bit of understanding of the vibrations. In the vibration, my dear friend, if any system is there, suppose there is a spring mass system is there, for example, we try to displace the mass from its equilibrium positions. We try to displace the mass from its equilibrium positions, from whatever the equilibrium position is there, where the net forces are zero, we try to displace that mass, and we will see that, okay, how this motion is happening. And that is what we call the natural frequency of the system, if there is no damper, right? How much of time it is taking to vibrate, to complete the cycles, right? Now, here also we will do in a very similar fashion. We'll try to disturb this structure. Sir, how can we disturb the structure? Now, just focus on this diagram. Just focus on this diagram. Now, in this, you try to understand, my dear friend, this column is being subjected to some kind of axial compressive load, as you can see. P amount of load has been applied to the material, and there is some kind of stiffness spring has been placed. Just to reduce the lateral deflection, what we have just done, we have done some kind of supporting in the form of spring, right? Bottom we have the support, and in the top we have provided the support in the form of spring force. No problem. You try to disturb it by the amount P dash. Once you try to disturb it, after disturbance, this P dash will disappear. It will not be there for the system. After disturbance in the negative x directions, what will be the positions? Let's see the position. The position will be somewhere like this. The position will be what? The position will be somewhat like this, where the load P has been applied. And now you disturb this body in the particular, this rod in the negative x direction, the spring force will operate in the opposite directions. That is known by what? The reaction forces that offered by the spring force, right? Now, so if I just take the moment about B point, this P load, whatever that is distance will be there, that I'm calling this to be X, for example. This is nothing but theta, and this, suppose original length was what? L. Original length was what? L. So X can be written as what? L into theta. Actually, X can be written as tan theta into L, right? But tan theta is very, very small, so that we can treat tan theta is almost equal to what? Theta only. So if I just take the moment about B point, summation of moment about B point equal to 0, that means we are discussing about the what? Neutral positions, right? Static position, static equilibrium for static equilibrium conditions. In the static equilibrium condition, what we do, my different summation of moment about any pinpoint to be 0, right? So what about the moment P into what? X in this direction? The spring force is what? Spring force into what? L, right? That has to be 0. L into theta. Spring force is what? K into X minus K into X is what? L into theta into L. That is equal to 0. So what you are observing? P is equal to what? K times of L. This P will be called as P critical, my dear friend. This P will be called as P critical. And what is its value? K times of L. Make a note of it. So if somebody will be asking you what is the definition, what is the proper definition of the critical load, what you will say? The maximum axial load that a column can support when it is on the verge of buckling is called as critical load. You only see yourself, if P will be more than P critical, if P is more than P critical or P is more than KL, you try to observe. If P is more than KL, what you are observing, my dear friend? The moment has been offered by the P will be what? Will be more or less? Will be more, because P is more than KL. Then if I just multiply with the X on both the sides, I will be getting, my dear friend, this P into X is a what? The disturbing force. K into L into X. Kx is a spring force into L. That is a disturbing force, restoring force. So let me write here once again. Restoring force, I'm calling this to be Kx, right? Disturbing force is nothing but P. Let me write not force, let me write movement. That is a good meaning over here. So as you can see, the disturbing movement is more, as if it is more, P is more than P critical, it will be continuously deforming like this. It will be continuously deforming. It will be continuously disturbing the system. So it is a not a stable system. If P is more than P critical, that is a not a stable system. If P is less than P critical, then obviously P of X will be less than P of what? K into L into X. Then obviously disturbing movement is what? Less than restoring movement. Then the beam will be what? The column will be what? Under stable conditions. In between stable and unstable, there is a one condition called neutral conditions, right? And your just value of the load will be just equal to KL. Then you can say that, okay, it is just about to buckle. The moment you just apply more than P critical load by 1 Newton also, it will buckle. It will be unstable, right? Because P is what? P is creating what? P is creating about this movement like this. It will further try to disturb it. But spring force try to bring back the system to the original conditions, right? That's why we are calling restoring movement, right? Similar kind of things you might have seen in the vibration also, right? Make a note of it. So we will try to catch some few points and we'll make a note of that. That is nothing but something, a maximum value of the load a column can support when it is on the verge of buckling will be called as critical load. Make an important point, very, very important. To understand the buckling of column, Euler, one of the scientists, a mathematician, he developed some equations for critical loads and he has just framed the formulas, right? We will discuss those formulas, not the derivation part. So you just note down critical load formulas. Critical load formula will be n square pi square EI divided by L square, right? Sir, what is the n? First time we are learning. It's better that you modify here itself this formula so that no confusion will be there afterwards once we will discuss everything. L effective means effective length of the column. Effective length of the column. That is called L into alpha. Alpha is nothing but end fixity coefficient. That means it depends on the end conditions. So many types of support we have, fixed support, we have the pin support, we have the free support. That means there's no support also. So we will discuss one by one, right? And will be, we are taking from 1, 2, 3, something. Now, what you're observing, first case we are discussing pin support. What is this? Pin support. Pin support. In pin support, what we are observing, the rod is there which is being supported bottom also at the top also, and it is being subjected to a compressive force like this. After application of the load, if P will be more than P critical, then the column will buckle like this. This is for n equal to 1. This is called fundamental mode of failure. Fundamental mode of failure. Right? When n equal to 2, into the formula, when you put same end conditions, L effective length is what? L into alpha. Alpha is what? Here is 1. For pin case, for case number 1, you can note down alpha is what? Alpha is equal to 1. For pin case, you can note down alpha is equal to what? 1. When alpha is equal to 1, then directly L alpha will become what? L effective will become what? L only. But n will be 2. It will buckle like this. Right? So these are the some of the very, very important points that you must understand regarding the buckling of columns. Now, the buckling of a pin and column, pin column in the first mode, when n equal to 1, is called the fundamental case of buckling, column buckling, right? That I told you, right? Now, one more thing, what we have discussed in our formula, that P critical formula, we have seen, right? P critical formula, n square pi square ei minimum divided by alpha square L square, because L effective we are writing, L effective is what? L into alpha. This is the formula. But you observe in the formula we have written I minimum, moment of inertia should be minimum. Remember, in the column will buckle about that axis about which the moment of inertia is least one. What is the basic idea of studying the moment of inertia, my dear friend? Moment of inertia we discussed. What is the meaning of moment of inertia? Moment of inertia is nothing but which deals with the rigidity of the structure. That means it will allow the resistance to some kind of change in shape of the body, or maybe we can say that the name itself is suggesting that moment of inertia, any movement will be there that will be restricted, right? So if I take the large moment of inertia, the column will not buckle. The column will buckle about that axis where the least moment of inertia will be there, about which the least moment of inertia will be there. So here, if I just talk about, my different, you try understanding. Here, this is the cross section, right? As you can see, this cross section is a rectangular cross sections. This cross section is a rectangular cross sections, where this particular axis is what? BB axis. This particular axis is what? AA axis. And if I just take the dimension, my different, the dimension I'm calling this to be width and depth. Width and depth. So if I just take the moment of inertia about IAA, then what you are observing, D into WQ divided by 12. And if I just take the moment of inertia about IBB, what you are observing? You are observing that the moment of inertia about IBB will be W into DQ divided by 12. T is more than W. So what you are observing, my dear friend? You are observing that IBB is what? More than IAA. So what is the least moment of inertia? The least moment of inertia will be IAA. Into the formula, we have to keep it, right? So buckling will happen about the weaker axis, not the stronger axis. About the stronger axis, it will just apply the huge amount of inertia, resistance to that moment. It will not buckle. It will definitely not buckle. So column may buckle about the weak axis. So you have to design according to the minimum moment of inertia, not the maximum moment of inertia. If you just design based on the maximum moment of inertia, it will buckle. The dimension may not be sufficient to resist the deformations, to resist the bending moment about the weaker axis, and it will fail. So there is no use of designing the column for the stronger moment of inertia, right? So these are the few points that is a very, very important for solving a good numericals, right? So we have discussed this one. These are the formulas. E is nothing but what? Young's modulus of elasticity of the material, least moment of inertia, unsupported length, whose ends are pinned. One more thing which is very important in case of column, that is for the purpose of design, we designed one radius of gyrations, right? Radius of basically what? Gyration is one of the very, very important. In the radius of gyrations, my dear friend, what you are observing, we define I is equal to what? A into R square, where R is nothing but minimum moment of inertia divided by area. R is what? Radius of gyrations or gyration, whatever you call. See, so what we are putting, P critical pi square EI, I minimum is what? A into R square divided by L square. Just suppose, for example, I am studying for pin-pin connection, so I am taking alpha equal to 1. Remember, if pin-pin support is not there, alpha will be different, right? So our basic formula is what? Basic formula will remain same, pi square EI minimum divided by alpha square L square into N. This will remain same. But for this to understand, we must understand alpha will be different for different types of supports in which column has been supported, right? Now, sigma is what? Critical stress will be what? P critical divided by what? Area. So pi square EI R square divided by L square. So pi square EI L square divided by R square. I'm calling this to be one term, that is a slenderness ratio. That is nothing but L effective divided by radius of gyrations or gyrations. Note down. S is nothing but slenderness ratio. It is a ratio of the effective length to the what? It is a ratio of the effective length to the least radius of gyrations, right? Very, very important. So final formula will be what? Critical stress can be written as pi square EI divided by what? Pi square E divided by what? S square. Very important. Now you might be thinking, sir, what is the purpose of studying this slenderness ratio? The purpose of studying the slenderness ratio is nothing but we can classify the column based on the value of the slenderness ratio, long column, short column, or medium column, right? So these are the this particular table is very, very important where each and every cases has been discussed. Pin column, as we have seen, alpha is equal to what? 1. Alpha here they have denoted by what? K. So I'm just taking alpha is equal to what? Same thing. So what is the critical load formula? Critical load formula is what? N square EI minimum divided by K square L square. Alpha is equal to K, right? Earlier, whatever we have done the notation like alpha, you can just take the same notation, right? Alpha is equal to K. K is nothing but 1 for pin, fixed like a cantilever support, and the free end, we have the what? Effective length will be 12 and the critical load will be what? 1 by 4th, right? When you just free the support, on the top side, we don't have support, little bit of load you'll require, to buckle it. That's why it is getting reduced by what? 3 by 4. That is 1 by 4th. We have the value of critical loads. Fixed column, lot of amount of load you need to apply. That's why it is 4 times. Remember, all these particular cases we are discussing, all the cases are what? Fundamental mode of failure. All the conditions are pertaining to our fundamental mode of failure. Fundamental mode of failure. Fundamental mode of failure, my dear friend. That means all the cases are we are discussing n equal to 1. If n equal to 2, things need to be modified. Things need to be modified. That means what are the modifications? Suppose, for example, this is a case, right? When n equal to 2, then the critical load formula will become what? 4 pi square EI divided by 4 L square for n equal to 2. For n equal to 2. This is for n equal to 1. N equal to 1. N equal to 1. N equal to 1. Getting my point? That is the second fundamental mode of failure when n equal to 2. First fundamental mode of failure, or we say a fundamental mode of failure, we say n equal to 1. Getting my point? One more thing is the fixed and pin column. One end is fixed one, like a cantilever support, and one is what? Pin support. Remember, in most of the textbook, you will find not this value. This is taken from the GATE, right? So here they have written 2.046, but in examination, when you put P critical as 2 into pi square EI divided by L square, that is also correct for this case, for D case. That means you can take K value as 0.707. That is also correct. 1 upon root 2. That is also correct. That is also correct. Right? Whatever the answer will be given based on this and based on this, both will be there in the range. So what we have done till now, the formula wise things we have checked out. Now let's focus our attention on the numerical part. Right? Now, as you can see, the first question is there in front of us. A rigid bar of the length L is supported by the linear elastic rotational spring. Remember, whatever we have done, that is an idealized structure. Idealized structure, my dear friend, not a real structure. You will not see the beam to be bent like this. You will see the beam to be bent like this, like a curvature only. But we have assumed that it is an ideal one where we don't have basically what? Young's modulus or EI flexural, whatever the flexural rigidity, EI value is being just stored at the one particular point, not spread throughout of its length of the column. Now, but you might be thinking one more thing. So here we don't have linear spring. Here we have the rotational spring. What is this? This is a rotational spring. So generally spring we have the two types. Note down. Spring we have the two types. One is linear spring. Second, we have the rotational spring. One is a linear spring. Second, we have the rotational spring. That means you might have seen this, this is a linear spring where stiffness is what, K, right? But we have sometimes some kind of, you know, symbol like this. This is a rotational spring. We just denote it by beta R, or in some of the textbook you will find KT. This is called rotational stiffness. What we call a rotational stiffness, right? What is the unit? Newton meter per radian. Okay, this is nothing but Newton per meter. Getting my point? Now, to analyze the basically what is the critical load, we must disturb the system. Let's disturb the system by the amount P dash. After that, P dash will be disappear. What will be the structure? It will form like this. Getting my point? Here the load P is there. Here it will be X, and this will be the theta. Now, so if I just draw the free body diagram, what it will do, the spring will say come back, and it will offer some kind of spring movement. What is the value? Beta R into theta. Newton meter per radian, into theta, that will be what? Newton meter only. So you just take the summation of moment about a point. What you're going to observe, my dear friend? You're going to observe that P into X, that is in the anti-clockwise direction. Moment of spring, that is in the clockwise directions, that is equal to 0. X is what? X is nothing but L into theta. When you just focus your attention on C, B dash B, and this triangle, So what you are observing? This is theta. So this particular triangle. Just wait. This particular triangle. XL. So what you are observing? Tan theta will be what? X by L. So theta will be what? X by L. So what we are writing? P into what? L into theta. Beta R into what? Theta equal to 0. So what you are observing? P is nothing but beta R divided by L. That will become what? Critical load. That will become what? That P will become what? Critical load. We are just maintaining the neutral condition, where it is not deflecting further, not it is coming back. It is just at the neutral conditions. And it is just about to verge. That means about to buckle. If P is slightly more than PCR, it will buckle. If P will be less than PCR, it will be what? Coming back to its original positions. Getting my point? So this will be the answer. Beta R divided by L. Right? Now, this is the one more question we have. The figures of the idealized, that's why they have mentioned idealized, right? In actual scenario, we're never gonna have the bending like this. That's why you are observing one more thing. What you're observing, this shape is not elastic curve shape. It is just like a rigid body, because we are assuming that this idealized structure or column to be just like a rigid column, right? A figure so idealized structure consists of two rigid bar. See, rigid bar, right? In that we have seen that bending will not be there. EI will be what? Infinity, right? The rotational stiffness is beta R. What is the critical load of this structure? For this case, again, we had to disturb the system from its original equilibrium conditions. So if I assume this is nothing but equilibrium conditions, so if I disturb it from here, so what will be observing? This will be the shape. It will be deflecting like a rigid body, Now, so what you are observing, you can take the above part or below part, whatever the part you can do, and you can take the analysis. You can consider like this, or you can consider this one. Both the portion you can take and you can do the analysis. I'm taking the above portion, C part and B dash part, and we are see at C we have the load P, so we are trying to shifting this load P here also. Spring will offer some kind of movement. Spring will offer some kind of movement, my dear friend. At the top, it will be offered some kind of movement like this. At the middle also, it will offer some kind of movement like this, right? And what we are taking summation of moment about B dash point to be 0. We are taking summation of moment about B dash point. Summation of moment about B dash point, we are taking what? To be equal to 0. So if I take the summation of moment about B point to be 0, what we are observing, my dear friend, try understanding. So this will be what? This will be L by 2. So P into X, that is the what? Clockwise. MC is the what? Anti-clockwise about B point. minus of MC minus of MB, that is equal to 0. Getting my point? X is what? Once again, I'm writing L by 2 into theta from this triangle. This will be theta, this will be theta. So what about the beta r? This movement will be what? Beta r into theta. But what about this? Beta r into, that is a very much interesting. Initially, what is this angle? 180 degree. What about the final angle? This will, this is theta, this is theta, this is what? 180 minus 2 theta. So what is the initial angle? 180. What is the final angle? 180 minus 2 theta. So what is the final deflections in the spring? The final theta dash will be what? 180 minus 2 theta. So that will be 2 theta. That is only the trick. That is only the tricky thing in this particular numerical. So P into L by 2 into theta, that is equal to beta r into theta plus beta r into 2 theta. So P will be what? P will be getting what? 3 beta r into 2 divided by L. So P will be what? 6 beta r divided by L. This will be the answer. So this is one of the important. See, this is spring. Initially it was what? Initially it was what? Which particular angle? Like a what? What we have? The final angle. See, initially this is nothing but the angle. If I just take, if I talk about C point, so you can just take the example. What was the angle? Suppose 180 degree, imaginary, I'm just assuming at the at this rod above the point C, we have imaginary, structure, rigid bar, which is making an angle about 180 degree. The final angle is what? The final angle is what? The final angle is what? You can just take the example of 180 plus this is what? 2 theta. So this will be what? 180 minus 2 theta, right? So what is the angle? Initial angle is what? 180 degree. Final angle is what? 360 minus what? 2 theta. So what you are observing, my dear friend? 2 theta minus 180 degree, or you can just take 180 minus 2 theta, right? So what you are observing? Cos 180 minus 2 theta. What you will be getting? Cos 2 theta only. So final angle is what? 2 theta. Or instead of doing this one, instead of doing this particular step directly, you can remember, one thing. See, this beta, this particular point B is very much clear. Why the angle is 2 theta? That is a clear. Initial angle is what? 180 degree between the two particular supports. This one and this one. 180 degree. What is the final angle? The final angle is what? Final angle is what? 180 minus 2 theta. That's why initial minus final, if I do, I will be getting what? 2 theta, right? But for what about this one? Initial angle is what? 0 degree, and the final angle is what? Theta. So the ultimately angle is what? Theta only. 1 theta only. That is only the trick in these questions. Getting my point? Similarly, here also what we have taken? Beta r into theta, because it's displaced by what? Theta amount. Initially 0 degree and final is what? Theta, right? The same thing we are doing for this case, but only the trick is beta, whatever the moment at B offered by the spring force, that will be a little bit tricky one. That's it. Now you can solve the same thing by taking the B dash and A point also. Same thing you can do by taking B dash and A also. Here there will be some moment A will be coming into the picture. Moment B also will be coming into the picture. Some kind of load will also be coming here. P load is coming, B point, and that is what it is coming. If it is not being the ideal one, then what would be the actual free body diagram? Actual free body diagram would be something like this. Let me show actual free body diagram. It would be something like this. P load P. There will be some deflection like this. First of all, it will be deflecting like this. There is a P. This is offering some kind of movement in which direction? Like this. So it will offer some movement like this. This is a bending movement. This is a bending movement, remember, right? And whatever the apart from other thing, remaining things will be coming. But in our case, we are taking bending moment to be 0 because we are focusing we are treating that EI will be concentrated at a particular point, not the spread throughout the length of the member, because it is the ideal one, not a actual one. Just for our understanding, what is the basically the meaning of column, buckling of column, how the stability will be related to that particular column, buckling of column. That is what we are learning through this idealized structure. Nothing much we are dealing with that. Our purpose is to get the p-critical. That's it. Then we will throw this idealized structure and we will be what? Designing our actual beam, actual column. Right? Now, see, this is a one type of another problem. Now, a horizontal beam of sliding support C. Many of you might be learning only the, two types of support. That is a fixed support, that is a cantilever support. And then we have the pin support, or we might have discussed the hinge support or some kind of roller support. But one more support is there, we call sliding support. Sliding support means, note down, very first thing, sliding support, which offer no CFOs, which offers sliding support means which offers no CFOs, my dear. It will allow the vertical deflections, but it will develop resisting movement. Right? Like in case of this one, like this case, what we have, my dear friend, here we have the hinge support. Hinge support movement will be zero. Movement will be zero, But here in this case, movement will not be zero. Here we have the movement. Here movement is what? About a point to be zero. Sorry. Here the movement will be zero. Here movement at a point will not be equal to zero. So you cannot use that equation where you have summation of moment at a point to be zero. Yes, you can use it, but you need to know that what is the resisting moment offered by the sliding support A. This is the roller support. Remember, this is the roller support. This is the sliding support. Both are not same. Both are different. Let's focus our case A. First thing, that is that this figure is for A. This figure is for what? B part. For A part, my different, what they are saying that sliding support, we are applying some kind of load Q. They are saying what is the Q value, that is a Q critical when the column will buckle in either of the, because of this particular Q critical, either of this column will be buckle. You only tell me when Q will be just equal to QCR, when the load in the member will be equal to what? PCR. Why I am writing with the equal PCR? Because both are made up of same material, same diameter, same geometry, same length is there, same pin connection. Here also pin connection, here also pin connection, right? And at a point, this will be this one. Now, summation of forces in the y direction will be zero. You can take, because here you have the reaction moment, but vertical force will be zero. Vertical reaction will be zero, because it is allowing the movement. If any support will allow the movement in that particular direction, there will not be any force, no movement. If movement will be allowable, no reaction moment. If movement is not allowable, reaction moment will be coming. So PCR plus PCR will be QCR. So what is the QCR? 2 PCR. That means 2 times of what? Pi square EI minimum divided by L square. Because it is a pin connection. So alpha will be what? Alpha or K will be what? 1. Getting my point? So these are the few things which are very, very important. Now, further what you are observing for B part. For B part, it is a very simple understand. This is the moment B, this is the D point, this is the B, C point, A point. There will be some reaction forces at a point. There's no doubt about that. They are asking what should be the values of M when it is just equal to M critical. When it is just equal to M critical, this load will become what? PCR, PCR. Initially, the load will be P only. But the moment, if it is, we are applying more and more amount of load movement, then automatically this P will be reaching to what? PCR, P critical value. Now take summation of moment about A point to be 0. Then what we are observing? M, that is equal to what? PCR. This distance will be what? D plus PCR. This particular distance is what? 2D. So what is the value of M? 3 PCR into D. And if final answer, if somebody want to know, 3 into D into pi square EI divided by what? L square. Once again, there is a pin-pin connection. Here also pin, here also pin, here also pin. Pin-pin connection, we're gonna have alpha or k equal to 1. So this type of problem they mostly ask in GATE examination also. So try to focus your attention on this chapter as it is very, very important chapter, right? Thank you all.